4 billion years of the Earth's history, the Sun used to be much hotter than it is now, and has got increasingly hot. But if you look at the temperature of the planet Earth, through proxy records or whatever, it hasn't changed as much as you would expect. In fact, it looks like it's regulated within limits. This particular graph is a bit vague as to what the limits are here, but let's say for argument, say they're 0 degrees and 100 degrees, so water is liquid in this phase, and either frozen or steam outside. If this was a dead planet, by now the temperature would be way too hot for life to survive. Yet somehow, over the last 3.8 billion years or so, it's been kept within something that looks like reasonable limits. Looks a bit like homeostasis in a human being or whatever, where we have mechanisms, internal and indeed external, that as humans we use to regulate our heat within our viability limits. It looks roughly like, conceivably, something similar is happening with the planet Earth as the external perturbing force, the change of the sun from faint early sun to much warmer sun now, has changed. And this actually is the Gaia hypothesis that Lovelock came up during Lovelock in the 1970s, saying that the planet as a whole, the interactions between the organic biota and the inorganic environment looks like it's regulated itself to bio-friendly conditions, a bit vague what that means, which looks like homeostasis of some kind. So the immediate question was how. And he came up in 83 or thereabouts, 82, 83, with this Daisy World parable. And it's a sort of parable, it's an artificial lifestyle model, simplifying like anything, where you simplify to 1 or 2 species of biota, daisies, that are black or white, and their viability is affected by the temperature, so we're just concentrating on one type of species, daisies, one environmental variable and one perturbation. And this is a simplified parable, but obviously one hopes to expand it to much more complex scenarios. And you're looking at the steady states of the dynamical system, this feedback loop. And the steady states get modified by the perturbing parameter, which is the sun. And so what we're interested in is for what parameter range of solar output is the biota viable, is the planet viable, is the planet, for instance, between 0 degrees centigrade and 100 degrees centigrade, as one example. So there are 3 types of things in this model. There's biotic variables, there's environmental variables, external perturbation, which are just daisies, temperature, and the sun in this particular case. So the talk plan is to give my subtly different, it's for practical purposes almost identical to Lovelock's definition, then simplify like crazy. So try and identify what the baby is and throw out all the bathwater so that all the superfluous complications, just find what the core mechanism is that produces, if there is one, this homeostasis. Having done that, carefully sometimes redefine the concepts of viability, hysteresis, Daisy World effect, or I call it Gaia regulation, in fact, which is subtly different from the way Lovelock defined them. Having done that, amazingly, it turns out surprisingly easy to generalize to complex systems from this really simple one. And that's the new stuff. And that's going to be the last 10% of the talk. So, my favourite Daisy World, I add 2 conditions. All variables in this world change continuously. There are no jumps. Seems reasonable. All variables in this world are bounded above and below. Units up on scale to 0 and 1. So, for instance, the biota, daisies, minimum number of daisies is 0, you can't have negative. And you can't shoot off to infinity because by the time the biomass of daisies is equal to the mass of the planet Earth, there's got to be a limit before you hit there. Mathematically, those 2 things turn out to have interesting consequences. So, Daisies affect the temperature either positively or negatively. Black daisies, because they absorb the sun, they tend to heat themselves up, their local environment and anything nearby. White daisies tend to reflect the sun and have the opposite effect, either positive or negative, both work. And in the model, the biotic things, daisies in this case, are affected by the temperature, the one environmental variable, by something that looks like what I call a hat function, because this is temperature on this axis. When it's too cold, everything's dead. Too hot, everything's dead. And there's some viability range here between 0.3 and 0.7, and maybe it goes to a maximum somewhere in the middle. For simplicity, at least at the start, I just draw this, what I call a witch's hat. But any kind of hat will do, it turns out, as long as you've got a viability range and things, the biota are unviable outside that range. Could be 0 degrees for ice and 100 degrees, 0 degrees for ice and 100 degrees for steam, if you've got organisms that require liquid water. So you've got the temperature affects the biota by what we call a hat function. The biota affects the temperature. The more black daisies there are, the more the temperature increases. So just got this circular feedback, and then might start off with a simple piecewise linear model. Okay. Looks simple, turns out to be really counterintuitive. A little bit of maths, but I translate them straight into diagrams. I said things change smoothly. Well, you have an equation look like this. The rate of change of the biota, dB by dt, equals a hat function of the temperature minus B. This is basically before that anybody else looking at Daisy World, general Logistic equations are a more complicated version of this. What does this mean in practice? Okay, let's look at the other part of the equation. B affects E. You've got a similar equation, dE by dt. This is a parameter which specifies the time scale, so I kind of set it to 1 or ignore it. Is some, well, it's linear, or actually a linear with upper and lower boundaries, because I said things were bounded, but for most practical purposes, just look at the linear range, what I call a sigmoid, a bit like a sigmoid with straight lines. So that's the maths. And it translates into null clines, which is the kind of key concept here to visualize what's going on. Let's look at how B is solved by E. I've got this equation here, which translates into what if the planet's in a particular situation where B is this value and E is this value here on the graph, then as long as you're above this line, which represents, whoops, that went a bit too fast. As long as let's just go back to the, okay. As long as you're above the line, dB by dt is negative, so the system will move continuously over time towards the null cline, the heavy line, the hat function. Whenever you're below the line, it'll move up to it. When you're on the line, dB by dt equals 0. So if you're looking for stable, if you're looking for steady states, it's got to be on that line somewhere. Ditto for dE by dt, you've got a different looking null cline. You've got exactly the same, the dE by dt is only 0 on this null cline. And this allows you to visualize what's going on very easily, because this is taken from a paper. You've got the null cline of B against E on this, E against B on that. Does that make sense so far? Okay. And B against E, E against B, hey, you can take that, flip it over, get the axes corresponding, and get those two null clines on the same graph, which looks like that. I've turned the other null cline into a heavy dashed brown line. So E will be stable, anywhere along this line. B will be in equilibrium along the heavy black line where they intersect. The interesting places, 3 places intersect in this particular example. And it turns out if you look at those intersections, that top one, analysing dE by dt and dB by dt, that's stable equilibrium. So it's a stable steady state. The next one, when you analyse it, turns out to be an unstable steady state. And the third one down here turns out to be stable. So it actually, ignore the grey lines here, this is taken from the paper. Look at where the heavy dashed line crosses the heavy hat function, and it alternates between stable and unstable and stable. Now, these dynamics are altered by the sun, the external perturbing factor. And mathematically, I can show it on the same sort of diagram by putting a p-axis here, and what's going to do, trust me on the maths, but look it up in the paper to work out what's going on. It shifts the hat function left and right. For a weak sun, it's equivalent to having the hat function over here. For a strong sun, it's equivalent to having the hat function over here. So for all the possible, as the sun varies, you can plot the stable and unsteady states for the mid-range, turns out to be there, and you can run the sun up, run the sun down in the model, and plot all the stable steady states and all the unstable steady states, and you finish up with this diagram. Okay, those are the stable steady states, and here, this is an unstable steady state. The system will never remain there for more than half a second. It'll shoot off to one of the other stable steady states. So there's an overlap here of 2 possibilities. This is stable with iota 0, extinction. This is stable with iota positive. This is from a paper. I've switched P round to the low to high here. And what you see is, that's the same picture redrawn with a hysteresis loop. So what happens is, if cold sun here, I'll show you the sun running up from cold values. And this is the resulting, and when it comes back again, it goes around the other side of the hysteresis loop. Okay? So there's alternative values here. What does this mean? It means that if the planet Earth had no daisies on it, only this range of perturbation sun output values would put the planet in the viability range between 0 and 100 degrees, say. But if you are approaching it round the right way from the hysteresis loop, means you've got to come from the right place to get to the top branch. If you're coming from the top branch, you can be viable all the way out to here. What's happening here is you're colder than is normally viable, but there are stable steady states with a sufficient population of black daisies to counteract, to heat the planet up so they're viable, provided they're there in the first place. So, as a consequence, you've extended the range of viability. You've got this fragile zone between upper and lower limbs of the hysteresis loop. And I'm going to define that as Gaia regulation, where you've got such a hysteresis loop with upper and lower values in that way, that extends the range of regulations. So, when does this happen? Well, crudely speaking, it depends on where the 2 null lines, in this case, intersect, and whether the null lines intersect in such a fashion that they intersect outside, on the brim of the hat, crudely speaking. Doesn't always happen. The slope of this particular null line depends on the strength of the interaction of biota on environment. And if that's weak, there's no way that kind of extends the range of viability. So, just if you're, this is all theoretical models here, if you want to build a model that does it, make the viability hat narrow and the interaction of biota on environment strong, and automatically you will see this Gaian regulation for free. It's a homeostasis for free in a sense. So, because of the circular logic here, okay, bit of rush. People get confused. One of the confusions is to say that, okay, if black daisies with a positive feedback give this regulation, surely if you reverse things, you will not get that. If you white daisies must do the reverse. Well, no, white daisies give you regulation the other side. Both black and white give you the regulation. There's a criticism of Gaia hypothesis called the lucky, basically accusing people of cheating and choosing the feedback signs to get what effect they're looking for. Not true. Another fallacy, Gaia works by regulating the planet temperature. Not true. Lovelock makes this mistake. Gaia works by regulating the daisy temperature. People think Gaia is optimizing something, perhaps biomass. No, nothing's optimized. Is there a fixed point? There's negative feedback, but it's not negative feedback control with a fixed point, so it worries control theorists. Crucially, there's this confusion between different things. Fitness, here's a graph of B biota against P, the parameter space of the weak sun versus hot sun. Fitness is on this axis. And quite literally, viability is on a different axis. And what the Gaian effect is doing is extending the range of viability. So it's very literally orthogonal, yet people confuse the two. So one version of this is to say baby chairs and tables being high is a virtue, being stable is a virtue. But they are different, and sometimes they're in conflict. So in particular, here's a confusion. In this particular scenario, the planet would be too cold for daisies to be viable, black daisies, if you only had one black daisy. But if you have a bunch of black daisies, there's a stable steady state there. So clearly it's the effect of the daisies to increase the local temperature that allows the stable steady state to exist. So in that sense, the heat from the black daisies has made this Gaian regulation possible. But any more heat brings you down this slope and makes the daisies less viable. There are less. This is biota, so there's less black daisies. So more heat makes it less viable. A version of that is if the black daisies evolve to be greyer, the slope of this line changes, they get fitter, but less Gaian regulation. Evolution works on short-term fitness, roughly speaking, so evolution will evolve daisies to be grey, if there's no constraints against that, and will eliminate the Gaia effect. So okay, am I 90% of the way through? About. So, I've tried to explain in subtly different ways from the traditional explanation what's going on with two variables, simple straight line null lines, and that's difficult to explain. Let's generalise. One way is by making the hat function and the other function wiggly rather than straight lines. Turns out it makes no difference, you get the same results. All you're interested in is where null lines intersect. And it turns out they're going to intersect. Again, you're going to get the alternating stable and unstable scenarios, steady states, but you'll likewise get this Gaian regulation. This is still in two dimensions, where the two null lines, basically this is just saying they alternate, stable and unstable, at least one stable fixed point. In 3D, the null planes are planes, but still meeting in an odd number of points. They alternate stable, unstable. In 117 dimensions, same result. The proof in the paper, a bit ugly, goes by iteration. If it's true in n dimensions, look at each n-dimensional slice of an n+1 dimensional hypercube. And because of the properties I've carefully specified at the beginning of continuousness and finite bounds, the properties turn out to carry over. And any number of dimensions, you get exactly the same results. So roughly speaking, I tried and had difficulty explaining what was going on in 2 dimensions. I could have given exactly the same explanation with 179 dimensional graphs on the board, and all my statements would have carried over. The hysteresis, likewise. The Gaia regulation, likewise. Simple argument shows that Gaia regulation can only be increased, never decreased. I gave you that argument with the simple 2D case. It's exactly the same argument with the 179 dimensional case. So in conclusion, whatever ecosystem you're looking at with hundreds of biotic species, hundreds of environmental variables, even many external perturbing parameters, any dimensionality, any feedback effects that alter the viability range. Some may not alter the viability range, but if they do, they can only be this Gaian looking like homeostatic effect, and never the anti-Gaian effect that the people who think Gaian theory cheats. Take-home messages. The circular logic of Gaia, even in the 2D case, is confusing. There are many fallacies, which is why I didn't try and talk you through it with 179 dimensions. Carefully define Gaian homeostasis as the increased parameter range of the external perturbation, in this case the sun, for which the biota are viable. Whenever you use that definition, what I've said holds true. And just pragmatically, if you're building models, this is the way to get strong such homeostatic for free effects. So the new part of this talk is the proof, almost by magic and waving my hands, that, hey, everything I said about 2 dimensions gets 179 dimensions. And the other...
Okay, so I'm nearly convinced, except for one thing. What you actually showed in 2 dimensions is not very different from the logistic equation.
It could be. I'd have to think that through, yes.
Okay. Now, in the logistic equation, the hat function makes a lot of difference. It depends if it's a hat, if it's a sign, how it ends over there, and in particular, how it is open, how it is broad. There's a parameter that decides on that, and on the base of that, it depends if the various points are attractive, or they go through a bifurcation, or they go through a cascade of bifurcation, or a chaotic system, and so on.
Yes. Okay.
You see the problem with all
I do
this?
See the problem. It doesn't apply here.
Wonderful. Can you please explain me why?
I do. I wasn't going to take the follow-up question.
Continuous versus discrete time.
It is, yes, it is the continuous. Thank you. Thank you very much. Depending on your start. It's obvious.
So what you're basically saying is that all biotic feedback is negative feedback, so long as there are not time delays introduced through abiotic variables.
Okay. The first part was all biotic feedback, there's negative feedback. Well,
In the limit.
those are the only ones you see. Transients, I mean, basically if you start the system off somewhere, typically there'll be positive feedback in there. But the very nature of positive feedback is that you run away from it.
It turns out, yeah.
And because I've carefully made sure things can't shoot to infinity, they're inevitably going to go to a stable steady state. And a point attractor in the way I've set it up. And you're absolutely right to say if there are delays are the sorts of things that can introduce interesting cyclic issues. But I've avoided that in my model here to avoid.
Delays, for example, through geological effects or
Absolutely, yes,
atmospheric
sure.
effects.
Yes.
Fred, we're going to have to actually move on to the next talk, so save us as well.